What if everything we thought we knew about the universe was incomplete? Not slightly off, not in need of a small correction, but fundamentally flawed. Imagine being told that the most successful scientific theory ever created, a theory that has passed every test for over a century, might not fully explain reality. It sounds impossible. And yet, that is exactly the possibility scientists are now being forced to confront. Let's start with something that has shaken the foundations of modern physics. The James Webb Space Telescope, humanity's most powerful eye into the cosmos, has been sending back data that doesn't quite fit. Not random errors, not minor inconsistencies, but patterns. Patterns that suggest something deeper is wrong. And at the center of it all is one name: Einstein. Albert Einstein's theory of general relativity, published in 1915, is often considered the crown jewel of physics. It reshaped how we understand gravity, space, and time. Before Einstein, gravity was seen through Newton's lens as a force acting instantly across distance. The Earth pulls the moon pulls the Earth, and everything follows predictable rules. Simple, elegant, and effective. But Einstein changed everything. In his view, gravity is not a force at all. It is the result of the curvature of space-time itself. Massive objects like stars and galaxies bend the fabric of reality, and everything else moves along those curves. Planets don't orbit the sun because they are being pulled. They follow the natural paths carved into space-time. Even light bends, not because it feels gravity, but because space itself is curved. This idea has been tested again and again. The orbit of Mercury, the bending of starlight during eclipses, time slowing down in strong gravitational fields, the detection of gravitational waves, even the imaging of black holes. Every one of these confirmed Einstein's predictions with incredible precision. For over 100 years, general relativity has stood unchallenged. Until now. The James Webb Space Telescope is revealing something unsettling. When scientists look at the universe with this new level of clarity, they are finding results that don't match what relativity predicts. Not in one area, but across several. Take gravitational lensing, for example. When light from a distant galaxy passes near a massive object, it bends, creating a natural cosmic lens. This effect allows astronomers to measure the mass of galaxies and clusters. According to relativity, the amount of bending should match the amount of mass present, including both visible matter and the mysterious dark matter. But Webb is showing cases where the bending is off, sometimes stronger than expected, sometimes weaker, and these differences are not random, they follow patterns. That suggests the issue may not just be about missing matter, it may be about how gravity itself behaves on the largest scales. Then there's the expansion of the universe. Space itself is stretching, pushing galaxies apart. This expansion is measured using something called the Hubble constant. But here again, Webb's observations don't align perfectly with predictions. The early universe appears to have expanded differently than expected. The discrepancy is small, but persistent, and in science, persistent problems are often the most important ones. And it doesn't stop there. Webb has also discovered galaxies in the early universe that shouldn't exist, at least not in their current form. They are too massive, too developed, too structured for their age. According to our models, there simply hasn't been enough time for them to form like this. Yet, there they are. Even the way light travels across vast cosmic distances is showing subtle anomalies. On their own, each of these issues might be explained away, but together, they form a pattern that is difficult to ignore. A pattern that points to a deeper question. What if our understanding of gravity is incomplete? There are several possibilities. Maybe Einstein's theory is correct, but not the full picture. Maybe it breaks down at cosmic scales. Or maybe we are misunderstanding the universe itself, dark matter, dark energy, or something even more unexpected could be at play. Or, in the most dramatic possibility, Einstein could be wrong. Not entirely, but enough that we need to rethink the foundations of physics. And if that's true, then we are standing at the beginning of a new scientific revolution. Because questioning Einstein isn't the end of the story, it's where things start to get interesting. In the next part, we dive into the theories scientists are developing to explain these mysteries, and what could replace one of the most beautiful ideas ever created. Because once you accept that something doesn't fit, the real challenge begins figuring out what comes next. We've established that the James Webb Space Telescope is uncovering consistent mismatches between observation and prediction. Gravitational lensing doesn't fully align. The expansion history raises questions. Early galaxies appear far too evolved. Light behaves in subtle but unexpected ways. These are not isolated problems, they form a pattern. And that pattern forces physicists into uncomfortable territory. So what happens if general relativity isn't the complete story? The first thing to understand is this. Modifying Einstein's theory is not simple. General relativity isn't just another model, it is tightly constrained by deep mathematical principles. You can't casually adjust it without breaking something else. Most attempts to tweak it lead to contradictions, unstable predictions, or results that don't match reality at all. Einstein didn't arrive at his theory by guesswork. He followed strict guiding principles like the equivalence between gravity and acceleration, and the requirement that physical laws must look the same to all observers. These ideas severely limit what alternative theories can exist. In many ways, general relativity is almost inevitable given those constraints. And yet, the data suggests something must change. One of the most studied alternatives is known as modified gravity, specifically something called F-air gravity. In Einstein's equations, a quantity called the Ricci scalar describes how spacetime curves. In these modified theories, that simple term is replaced with a more flexible function. It may sound like a minor adjustment, but it changes how gravity behaves across different scales. At small scales, like within our solar system, these models can mimic general relativity almost perfectly. But at cosmic distances, they begin to diverge. That means they could potentially explain why the universe expands the way it does, or why gravitational lensing appears inconsistent without needing entirely new forms of matter. Another approach introduces entirely new fields into the picture. These are called scalar tensor theories. Instead of gravity being purely geometric, an additional scalar field interacts with matter and influences gravitational behavior. In some versions, even the strength of gravity itself can vary over time and space. These theories are powerful because they can be tuned to match both local experiments and large-scale cosmic observations. They offer flexibility, but that flexibility comes at a cost. The more adjustable a theory becomes, the harder it is to prove it's actually correct. Then there's an even more radical idea. What if gravity itself has mass? In standard physics, the hypothetical particle that carries gravity, the graviton, is massless. That's why gravity has an infinite range. But if the graviton had even a tiny mass, gravity would weaken over vast distances. At smaller scales, everything would look normal. But across the universe, the rules would shift. Building a consistent theory of massive gravity took decades because early versions led to serious theoretical problems. Only recently have physicists found ways to make these ideas stable. And now, they are being taken seriously as possible explanations for cosmic anomalies. But perhaps the most fascinating idea goes even deeper. What if gravity isn't fundamental at all? In emergent gravity theories, gravity is not a basic force, it arises from something more fundamental, like information, entropy, or quantum interactions. In this view, gravity is similar to temperature or pressure. It's not something you can isolate, it's something that emerges from deeper processes. This concept has roots in earlier work showing that Einstein's equations can be derived from thermodynamic principles. Some physicists have taken this further, suggesting that what we interpret as gravitational effects could actually be the result of underlying microscopic behavior. If that's true, then the anomalies seen by James Webb might not be flaws in gravity, they might be clues about its true origin. And finally, there are theories involving extra dimensions. According to some models inspired by string theory, our universe may have more dimensions than the four we experience. These extra dimensions could influence how gravity behaves, especially at large scales. If gravity can leak into these hidden dimensions, it would appear weaker or behave differently across cosmic distances, potentially explaining the discrepancies we observe. Each of these ideas is an attempt to answer the same question. If Einstein's theory isn't enough, what replaces it? But proposing alternatives is only the beginning. The real challenge is proving which, if any, of these ideas is correct. And that's where things get even more complicated. Because even if we have multiple possible explanations, science doesn't move forward on possibilities alone, it moves forward on evidence. Right now, the observations from the James Webb Space Telescope are suggestive, but not decisive. They hint at inconsistencies, but they don't yet point clearly to a single solution. That means physicists are left with a difficult task, finding ways to test these competing ideas and determine which one actually describes reality. And that's not easy. The first approach is straightforward. In principle, gather more precise data. Webb has opened the door, but it's only the beginning. Future observatories, both on Earth and in space, will map the universe in even greater detail. They will track how galaxies cluster, how light bends, and how cosmic expansion evolves over time. If general relativity is truly incomplete, these discrepancies should become clearer and more systematic. If, on the other hand, the theory is still correct, then improved measurements might reveal that the problem lies elsewhere, perhaps in our understanding of dark matter or observational limitations. Another powerful method comes from gravitational waves. These ripples in space-time, first directly detected in 2015, provide a completely different way to test gravity. When massive objects like black holes collide, they generate waves that travel across the universe. According to general relativity, these waves have very specific properties: their speed, their polarization, their energy distribution. So far, every detection has matched Einstein's predictions remarkably well. But as detectors become more sensitive, they may begin to pick up subtle deviations. Alternative theories of gravity often predict small differences in how these waves behave. Even a slight inconsistency could point toward new physics. There's also the possibility of detecting deviations much closer to home. Experiments within our solar system have already tested general relativity with extraordinary precision, but no measurement is perfect. As technology improves, scientists are designing experiments that can probe gravity with even greater accuracy using atomic interferometers, laser measurements between Earth and the Moon, and highly sensitive torsion balances. If modified gravity affects large scales, it might also leave faint signatures, locally signatures we simply haven't been able to detect yet. But beyond experiments and observations, there's another path forward: theory. Sometimes, the biggest breakthroughs don't come from new data, but from new ideas. A single insight can reshape an entire field. Einstein himself developed general relativity largely through thought experiments and mathematical reasoning before it was fully tested. It's possible that we are on the edge of a similar moment. A new framework could emerge, one that naturally explains both the success of relativity and the anomalies revealed by Webb. Or it could unify gravity with quantum mechanics, something physicists have been trying to achieve for decades. Because at the heart of all of this lies a deeper issue. General relativity describes gravity on large scales, while quantum mechanics governs the smallest scales. Both theories work incredibly well, but they don't fit together. They describe reality in fundamentally different ways. If Einstein's theory is incomplete, it might be because it's only part of a bigger picture. And that brings us to a much larger question. What does it actually mean if Einstein was wrong? Not just slightly off, but incomplete in a way that forces us to rethink space, time, and the structure of the universe itself? Because the implications go far beyond physics equations. They reach into the very nature of reality. Because if general relativity is not the final answer, then our understanding of space and time themselves may need to change. Before Einstein, space and time were seen as separate and absolute. Space was a fixed stage where events happened. Time was universal, ticking the same way everywhere. This view felt intuitive, almost obvious. It matched everyday experience. Then Einstein showed that both ideas were wrong. Space and time are not separate. They are woven together into a single fabric called space-time. And this fabric is not fixed. It bends, stretches, and evolves. Different observers can measure time differently. Events that seem simultaneous to one observer may not be to another. This wasn't just a new theory, it was a new way of thinking. And now, we may be facing another shift just as profound. If the anomalies observed by the James Webb Space Telescope hold up, they suggest that space-time itself may behave differently at cosmic scales than we expected. The smooth, continuous fabric described by Einstein might be an approximation, a useful model that works in many situations, but not all. One possibility is that space-time has a deeper structure, something not captured by current theories. It might emerge from more fundamental elements, just as temperature emerges from the motion of atoms. In this view, space-time is not the base layer of reality, it's a higher-level phenomenon. That idea is both exciting and unsettling, because it means the geometry we rely on, the curves, distances, and trajectories may not be fundamental truths, but approximations of something deeper. It also raises questions about causality, the relationship between cause and effect. In relativity, the structure of space-time determines what events can influence each other. But if space-time itself changes at large scales, those relationships might shift as well. Even the concept of gravity could be redefined. Instead of being a geometric effect, it could be the result of microscopic interactions we don't yet understand. It could depend on information, entropy, or quantum entanglement. These ideas are still speculative, but they are being taken seriously. And if they turn out to be correct, the consequences would be enormous. It would mean that everything built on general relativity, from cosmology to black hole physics, would need to be revisited, not discarded, but reinterpreted within a broader framework. This is how science evolves. Newton's laws weren't wrong, they were incomplete. They work perfectly in many situations, but they break down at high speeds and strong gravitational fields. Einstein didn't destroy Newton's work, he extended it. In the same way, whatever replaces or modifies general relativity will likely include it as a special case. But the shift itself could be just as dramatic, because it changes how we think about the universe at the most fundamental level. And when our understanding changes at that level, It doesn't just affect physics, it reshapes our entire perspective on reality. Consider what's at stake. General relativity underpins modern cosmology. It's the framework we use to describe the Big Bang, the expansion of the universe, the formation of galaxies, and the behavior of black holes. If that framework is incomplete, then our interpretation of all these phenomena may also be incomplete. Take dark matter and dark energy, for example. These two concepts were introduced to explain observations that didn't match predictions. Galaxies rotate too fast, so we assume there's unseen mass holding them together. The universe is expanding faster and faster, so we introduce a mysterious energy driving that acceleration. Together, dark matter and dark energy are thought to make up about 95% of the universe. And yet, we've never directly detected either one. That raises an uncomfortable possibility. What if they don't exist in the way we think they do? What if they are not real substances, but signs that our theory of gravity is incomplete? Some alternative models suggest exactly that. Instead of adding invisible components, they modify the laws of gravity themselves. In these models, the extra effects we attribute to dark matter and dark energy emerge naturally from the modified behavior of gravity. One example is modified Newtonian dynamics, or MOND. It proposes that gravity behaves differently at very low accelerations. This idea can explain the rotation of galaxies without requiring dark matter. But MOND has its own challenges. It struggles to explain other observations, like gravitational lensing and large-scale structure formation. That's why newer theories try to combine modified gravity with additional components, creating hybrid models. The observations from the James Webb Space Telescope could play a crucial role here. If the discrepancies continue to grow, they may point toward a consistent pattern, one that favors certain theories over others. They could reveal whether dark matter is real or whether it's an artifact of using the wrong equations. And that would be a turning point, because it would mean that for decades, we've been building our understanding of the universe on an incomplete foundation. Not wrong in every detail, but missing something essential. And that realization brings us to a moment that is both uncertain and extraordinary. Science doesn't move in straight lines. It advances through challenges, contradictions, and moments when the data refuses to fit. These moments are not failures, they are opportunities. They force us to question assumptions, refine ideas, and sometimes rethink everything. Right now, physics may be standing at one of those moments. The James Webb Space Telescope has not proven Einstein wrong. That's not how science works, but it has raised questions that cannot be ignored. Questions about gravity, about cosmic evolution, about the nature of space-time itself. And those questions are powerful, because they open the door to discovery. In the coming years, new observations will test these ideas with increasing precision. New theories will be proposed, challenged, and refined. Some will fail, others may succeed. And slowly, piece by piece, a clearer picture will emerge. It may confirm Einstein's theory in a deeper way, or it may reveal something entirely new. Either outcome would be remarkable, because what we are really witnessing is not the fall of a theory, but the evolution of understanding. Einstein transformed our view of the universe once before. If his theory turns out to be incomplete, it won't diminish that achievement, it will build on it. And perhaps, somewhere right now, a new idea is forming. An idea that will explain these anomalies, unify the laws of physics, and redefine how we see reality. If that happens, we won't just learn something new about the universe. We'll learn something new about the limits of human knowledge and how far we can push them. And that's what makes this moment so fascinating. Because the story isn't over. In many ways, it's just beginning.